So what would be our objective, our aim of this class and maybe the session. After the session, we will keep on doing Markov chain and Markov processes. At the end, the results that we will do, we will apply them to know how to learn about this meaningful algorithm on which the Google is working, for example. It's called the page rank algorithm. So our task, we can say, key task would be to get into that algorithm and learn it, see as an application. How is very basic problem today. It's being applied to a lot of very so we'll get into the page rank algorithm. Now we went into the page rank algorithm, especially when we had done function analysis, but we answered a different question here. So what we answered through six-point theorem was that if you give me a word and that word appears in a bunch of websites, okay, why the ranking of such websites must exist? There was an existence problem. Roughly, went into mechanics of page rank algorithm. We didn't talk about it in a sophisticated manner, but we will do it. So Markov chains are important, they are everywhere, especially in finance and also looking at some of the papers. There's strongly in physics as well, so as opposed to of the beautiful papers written basically on physics and also physics, where you are trying to explain lots of things about chains and about the process. These are one of the very most bits like evolution from calculus, but I want to do it. I think it does. So what we are interested in, roughly, we are interested in knowing the long-term behavior of, say, a sequence of random variables. Okay. May also question. We already know the theorems actually, which allows us to basically say things about that what would be the behavior of the sequence of random variable or a stochastic process in long run. For example, you have the central limit theorem, you have the law of large numbers. Okay. Basically, roughly say that okay, what will be a sequence of random variable in long run. Okay. But the key thing in these two theorems, like law of large number or the different versions of central limit theorem, is that you assume that your sequence of random variables is kind of IID actually. They are independent and identically distributed, which is a huge assumption actually. Okay. So what Markov showed that you don't need this assumption, and you can still study the long-term behavior of the sequence actually. Okay. So useful in our processes. We'll get into our major focus will be basically, that if you give me a well-behaving process, whether a Markov process or a Markov chain, what would be its fate in the long run actually? That's how we learn. Okay. Obviously, for getting into, for achieving any objective, you have to get into it. You have to make your hands dirty in theory. There's no shortcuts. You have to get into details, examples, and so what we said, imagine that I have a, so not, just repeating everything that we did, discussed in the last class. I'll just give you a quick review of what we did. So if we did that, if you have a stochastic process, okay, but this time we assume that this stochastic process takes values in a set actually, what do you call it? State space, okay? So I know that in stochastic process, every extend is a random variable which takes values. whatever xn takes values are from this set as and then you call such kind of a process, a Markov process or a Markov chain, okay, if it's a memoryless process. In other words, a memoryless process, that it's a process in which the future depends on the present and not on the history. Okay? In other words, if you want to say that, what is the probability that xn takes a value xn, and given that you know everything about this process, we have a realization of the process that at time naught it was naught, x naught, and at time x1 it was x1, and so on and so forth, and at time xn minus 1, it has the value xn minus 1. So this is like present, okay? And this thing is like history, okay? And xn equal to x is like the future that I'm interested in. So in other words, I'm interested in computing what is the probability or what would be the future of this process given that I know it's present in history. Okay? So a process is a Markov process, a Markov chain, if this probability is same as the probability that xn is xn given that xn minus 1 is xn. Okay. In other words, this history does not play any role. And we discussed several examples. We'll discuss more examples today as well. But one of the key example that we discussed last time was what we call this random walk activity. That if you have a sequence of independent random variables, okay, then the random walk, in other words, imagine you are playing a coin tossing game, and you win, you get $1, and you lose, you give up $1. Then the Zn, okay, which is going to be the sum of money after the n games, is going to be what? It's going to be, Zn minus 1, the money that you have, on n minus 1 game, plus, whatever happens on the n game. So I'm denoting that by Ln, and this Ln can be 1 with the probability of E, and it could be minus 1 with the probability of minus P. Okay? So this Zn is roughly a random walk. I just studied it previously. We also talked about it that this random walk is basically a Markov process. The other example that we said that if say xn represents the weather, okay, on the nth day, and we started say looking at the weather. I mean, if you're talking about an hour, for example, or if about a day, then you can say that okay, xn is the weather in the nth hour. But I can also talk about year actually, that's in the weather hour. And then what potential values it can take? So xn. So in other words, what could be the state space for this? So the weather could be what? Dry. So it could be wet. Okay. But if you assume, for example, you can put other basically kind of states as well. But for the simplistic example, I can say that there's weather is dry, or it's wet, or it's rainy. And each of this xn is going to take And each of the day is going to take one of the parameters here, and we'll solve that. Okay, this is the market. Folks who had this question on your exam as well. All right, and then we talked about what we call the transition probabilities. So transition probabilities. What do you mean by transition probability? Imagine you have a state space S, and you are saying that imagine at an instant n, the state of on an instant n, the value of the process that it takes is I. What is the probability that it after the what you call n movements or n days or whatever it is, or n gains, whatever context you are talking about, or n steps actually will be the n plus n, it will be in state j. Okay? Where I and j are two what you call states. Okay? So it's like that's a probability of transitioning from the state I to the state j. Okay? And we denoted this probability by Pi. Okay. So mainly this would be one of for a given scenario, situation, process. Okay, this will be one of one of the objects that will be interested in. And what we can do, we can make a matrix out of it. If I have, for example, this matrix Pij, where I and j are from this S, then this matrix is what we call a condition matrix. What are the key properties of the matrix? This matrix is that it's a stochastic matrix. Stochastic matrix. So we have a stochastic matrix. All of the Pijs are non-negative. Okay. Nothing has a negative probability. And if you in this matrix, if you sum up the roller, we call them if you sum up all probabilities in a row, you always get a number. We call such matrix as condition matrix. So if you have been given a process, the first thing will be that you should care for is that what is the transition matrix for this? That this is your other. Okay. Then, I am also defining J with the superscript n. This must be and the idea is what? It's the probability that on n minus 1 moment on currently you are in the state I, and in the next moment you will be in the state j. So what I wrote previously is something else. Okay. So what is Pij? And in other words, what is the probability that you start from the state I, okay, and you after the n steps you end up in the j. So this is the probability reach from transition from the state I to j in n steps actually. Okay, n steps. You make sense of the steps. Steps, for example, in this context, step is a gain. So in this weather contest, this step is a day or hour or whatever. This is, and the collection of all such transition probabilities, in other words, collection of all such transition probabilities that I and J are from the state S, give it a name, the transition matrix, but the superscript N. I'm putting it in the bracket because you shouldn't consider it to the power. It's not power. For the simple, it means that can you reach from the state I to J in the collection of all such probabilities. Let me give you an example. Useful and an interesting way to write such kind of processes, especially when your state space is finite, is to make a picture of it. Nothing about Markov chains and see that you can really visualize. So imagine I have we are saying that imagine I have a process Xn and a state space in which there are 4 states, right? And imagine someone told me the transition matrix for it. The transition matrix looks like this: 0.8, 0.20, it's 0.40, 0, 0.5, 0.1, 5, there must be a 50 space. Say 1, 0, 0, 0, 0, 0, 0, 0.5, 0. Any matrix. Just make sure that the sum and the rule is 1. It's not necessarily the column. You just have to use one convention. Yes, you can use the convention that the columns has some 1. Just stick with one convention. One convention. They just assume that the rules have some. So what you can do with this matrix is what you can do is that you can make a presentation out of it. What will be there? So this takes let's take it as 1 and 2, say 3, 4, and 5, for example, these are the states. So what this first number is telling you that what is the probability that today I am in the state 1 or n minus 1 is state n minus 1th movement. Presently I am in the state 1 and I will stay in the state 1. The probability is 0. And what are the so I will go from 1 to 2. Okay. I don't need to put anything because
cannot do.
Probably once you because the probability is 0. So in other words, if you are at 1, you are stuck between 1 and 2. So you can't go anywhere else. Okay. And you have 2, 1. You can imagine that. You can say, imagine these are the 5 places in the Sukkur which are offering, for example, pizzas. Okay? Which make pizzas. I'm sure more than 5, but let's assume they are 5. Then this matrix is kind of representing what? So point 8 is representing that imagine you visited, today, Pizza Town, Pizza Hut, and tomorrow or the next time you roam again visit. Chances are 0.8. What do you mean by 0.1 to 0.2? So it's like state 1 to state. This time we visited state 1, and then next time we visit basically the state 2, the chances of happening are very low. And 0.4. So you can make a picture out of it. Now just quickly making pictures of how is it going to look like. So 2, 1 is 0.4, 0, 0, 0. So this is what? 2 to 4. 2 to 4 is 0.5. Okay. And what? 2 to 5 is 0.1. So you can already see that basically you're going to get some picture out of it, something like that. So what you can do is basically, so what you have is that you have a finite state Markov chain representation. We have this representation of a Markov. What if you have, say this state, this process, marking process of the chain, which you can have only 2 states out. Okay. You have certain probabilities. So how does the Markov the picture of this is going to look like? So you're going to have the 2 states, I and other. Okay. And imagine you have been given, for example, suppose you solve this in exam, that probability that you will have, it will be wet tomorrow and it's dry today is say 2/3, and the probability that it will be what? Dry tomorrow, okay, and it's wet today is we call 1/4. And from this we will also compute what would be the probability that it's dry today and it is still dry tomorrow. It's wet today and still dry tomorrow. So going from this to this is what? 2/3, and going from dry to dry to wet is 2/3, yes, and we can 1/4. Okay. So you can have a such kind of system. Are you going to compute these probabilities?
1 minus is.
You can have.
This are you state. Because either you can have dry or wet.
So you can say that imagine you have yes, you have dry or wet.
So first you know the probability of wet, then you can
So you know how to compute it. So you really use what you call the law of probability. Okay. But I just don't want to stick with, say, 1 minute of the time. In other words, so I'm not interested in only that what would be the weather tomorrow. How about if I'm interested in what would be the weather after the 10 days? Okay. Or what would be, say, for example, when you search on Google, what would be the weather of a Sukkur? So they have a prediction set. They already have, defined states in which the weather can be. The question is, if I'm interested in computing the probabilities of it, how can I compute it? In other words, imagine I have a Markov chain. Okay. Imagine I have a Markov chain. Xn. Maybe other things, the chain of it can represent the state of the weather of the Sukkur actually. And I'm interested in, for example, the probability that this weather today, for example, it's X0 from even in like X time. Okay, feels like it could be not necessarily today, but you can say that imagine it's a prediction about the upcoming n days actually. Okay, so x naught is x naught say, and x1 is x1 and so on and so forth, and xn is xn. Okay, so we have the n days. If you are interested in computing, for example, probabilities, in such probability. The question is, can you visualize this actually? What would be the interpretation of this actually? Okay. So the interpretation of this, so this could be like a week actually. Okay, a week. And the 7, so this is like a week actually. So you are interested in, that okay, you are interested in computing the probability of a particular event that, what is the probability tomorrow you're going to have this, or today you have this, and tomorrow this would be this, and day after tomorrow would be this, and after the 7th day would be this. So you're looking at what you call the predictions by the Google or the others. The question is, how can I do it? The only thing that I know about it is that this xn is a Markov chain.